Okay, what numerical relationship exists between moles and particles? Remember, particles come in three flavors: atoms, formula units, and molecules. Avogadro's number. And whenever you're converting from moles to the particles, does Avogadro's number go on top of the fraction or on the bottom? Are you guys just guessing and shooting in the wind, or do you have a reason? Okay.
It has to cancel.
What has to cancel?
The moles.
Moles has to cancel. So tell me what goes, since we know we have moles and we're going to particles, tell me, I already have it written here actually, one mole goes on the bottom. So if we're going to particles, the particles number has to be on top. So Avogadro's number has to be on top. Do not just say an answer, think about it, right? You know you have to cancel moles, so it has to go on bottom. So you're going with 6.022 times 10 to the 23rd particles, or whichever one of these three that you're talking about, that is going to go on top. And that's because mole has to cancel with mole on the bottom. So the way I've set it up here is I have mole is what we're starting with, and we're going that way. But we could easily, just as easily, go the opposite direction, but we'd have to flip the fraction. So tell me the relationship between mole and molar mass. And I have an example of potassium here. It's hard to see, because sometimes people are like, I don't know what to do if I'm not given an element. I'm just going to go ahead and give you an element for potassium. What's the relationship between mole and mass?
Grams on top.
Yes, grams on top. What number of grams for potassium in particular?
The atomic number for the atomic mass.
Okay, so the atomic mass is 39.10 grams per 1 mole. So the mole cancels. You always guide yourself with the mole being the first thing actually in this example. Mole goes on bottom, cancel, cancel. Grams are on top. You get 2 grams of potassium. That number is not a standard number though, right? That number is different for every compound, every element, or it's a summation of multiple elements together. Okay, the last relationship, so we had particle number, we had mass, and our last relationship is to volume, and that volume is called molar volume. What is that number? 22.4 what? Liters. And so if I'm going from moles to volume, does the 22.4 liters go on top or on bottom? Top. So 22.4 liters there per 1 mole. So the moles cancel, and you get yourself to liters. Okay, so that's the 3 mole relationships to learn. That's it. But we also know that there are this is like obviously super simple because it's a single step problem. But there can be ones that have 3, 4, 5 steps within them. So I want to go over one of them. I think it was the one of dichlorine on problem set. What was your question on problem set?
It's more like a one-on-one thing. I feel like I'm doing this, like I had some more.
You want to give me a specific example, or do you want to just
like, well, on the second one, I just like I got something like I feel like I didn't grasp how to do that problem. Well, there was how many molecules of water and 5 grams of water.
Okay, so how many molecules of water are in 5 grams of water? Okay, so this is number 2?
Yes.
Write this down if you don't have number 2 down. Okay, so you're starting, the question says to go to molecules. So molecules is one of the 3 particles. So if you think about it, what number should be used eventually in this process? Avogadro's number should be used eventually, but probably not the first step, because you're starting off with grams of water. You can't do anything with grams. You have to get to the stepping stone of moles. So if you're starting off with water, grams, what unit should go on bottom? Grams of water. I always start off with writing the denominator, because if I see my unit here, I immediately have to cancel that. I know that, so I'm going to go ahead and put it on the bottom. But I'm going 2 moles, so I'm putting moles of water on top. And what number usually always goes within the conversion factor with moles? 1. And then what goes with water? 18.016, because that's H plus O. So that's something you just calculate. And if you calculate enough, you start to memorize these things by accident. Okay, so grams of water go away. So it's not unusual to see multiple step problems. This one is one of them. So then you want to get to molecules.
Are we doing, like, I know this is a 2-step thing, so now we're going to grams?
No, we just got out of grams. We actually already got out of grams. Now we're in moles. So this is the unit we're looking at now. So how do we get from moles?
But how did we cancel the 5 grams?
We haven't actually calculated, so usually the first setup part is just like look at your units to make sure all the units cancel, and then the very last step means we'll plug the numbers in to calculate. We actually haven't calculated anything yet. We're just converting to the mole unit.
But is the 18.06 the mass of?
A mass of H2O because we added that up. So we in our calculator, we would, if we wanted to stop here, we would do 5 divided by 18.16. But we're not there yet. We need to take our moles to molecules. And what's that conversion? Or what's my setup here?
A mole of H2O is on the bottom.
So 1 mole of H2O is on the bottom because I have the relationship between 1 mole of water to particles is what? What goes on top? So Avogadro is 6.022 times 10 to the 23rd molecules of water. Okay, so then our moles of water here and here cancel, but we literally still haven't calculated anything. We just need to now check everything units. Is it right? Yep, molecules of water are there. So then we would do 5 divided by 18 times Avogadro's number. And whatever that is our answer. Pull out your calculator for me.
It's 1.67.
Thank you. Times 10 to the 23rd molecules. Okay. Side note, this is a question that somebody asked me earlier. What if I had given you 14 molecules of chlorine gas? 14 molecules of chlorine gas. Is that chlorine gas? No. Cl2 is diatomic chlorine gas, right? Chlorine gas is Cl2. How many atoms of chlorine are in 14 molecules of Cl2 gas? So we're just trying to like do some math in our head, but we have a process, right? The dimensional analysis is our process, our go-to process. We have to use it. Because if not, you're accidentally going to divide by 2 or multiply by 2, something that you didn't mean to do. This is going to force you to ensure that it's always correct. So what unit has to go on bottom? So remember my question was atoms of chlorine. What goes on bottom? I need to cancel molecules. Molecules are not moles. Molecules are a tangible item, right? I have a diatomic chlorine molecule. It looks like this. There's chlorine. That's it. That's diatomic chlorine. How many atoms of chlorine are in one molecule? 2. Yeah. So here's a molecule of chlorine. There's an atom of chlorine and there's an atom of chlorine. Okay. So molecules must go on bottom because that's what I need to cancel. So 1 molecule of chlorine gas has how many atoms of chlorine in it? 2 atoms of chlorine. So I don't think I heard any right answers when people were saying it earlier. What's the right answer? 28 atoms. Chlorine. So you've never had to actually work before, I don't think, in any science class. This is the first time you've had to work and show your work. So you've got to get over the fact that you don't want to do it. You need to do it to get the right answer. You need to say molecules cancel to get to atoms. That means I have 28 atoms. I know some of us are like, oh yeah, there's 2 atoms of chlorine per molecule of chlorine. Yeah, you can do that in your head, but when it gets more complex, you're going to need a process, and this is the process. It's not magic, it's math. Okay? I'm just giving us a heart to heart here. You've got to do it. All right, so any more questions right now? I promise at 10. Yeah? I just made that up. I said, if I had 14 molecules, tell me how many atoms would be there. That was a tangent example. Yeah?
Can we do number
3. Will you read it to me?
how many moles of lead to oxide?
Moles of what?
Lead to oxide.
Oh, oxide. Are in what?
Are in 3.50 times 6.
Okay, this is number 3. So if you've not done number 3, please participate. So if you're given a particle, you're given 3.50 times 10 to the 26 particles, aka 4 million units in this case, of lead-2 oxide, and you want to get to moles. First step is to think, is there a relationship between particles and moles? Yes, and what is that relationship? So Avogadro's number, right? So the very first thing you should say, can I convert directly there? In this case, it's a yes, because this one is going to moles, and that's usually our first step anyhow, so this is a one-step process. So if I want to cancel 4 million units, I have to put them on bottom. So 4 million units of lead-2 oxide. How did I know that was lead-2 oxide, by the way? The 2's cancel out, right, okay. So that number is 6.022 times 10 to the 23rd. 4 million units per 1 mole. So that per 1 mole is just on top of this. And that, again, we need to make sure we set up the denominator first so that we can cancel out formula units and formula units. And in your calculator, you would put big number in parentheses divided by another big number in parentheses. 581 moles. Okay, sounds good. I'm sure that's right. And the answer's in the bottom, so you guys can check that. The answers are on the bottom of that, yeah. Okay, what if instead I'd said go to atoms of oxygen? Instead of going to moles, I wanted you to get atoms of oxygen. What would you do from this step here? Formula units of lead 2 oxide. Anybody? Go for Jason.
You take one atom of oxygen on the top, yeah, two
I have to cancel this, right?
Yeah,
So I have one formula unit of lead 2 oxide. So one thing of lead 2 oxide, one particle of lead 2 oxide has also one atom in it. So that actually is the same number, 1 over 1, right? So 3.5 times 10 to the 26 atoms of oxygen. So the formula unit part, I think some people are like, what the heck is that? It's just a subunit of an ionic compound. It's like a molecule, like a particle, like an atom, but it's just called formula unit, just because it's a specific term for an ionic compound. Okay. Keep problems set 10 on your desk for now. And hold on to it, because I just want to see those of you who have made progress, because it helps me figure out where we are. Before we do notes, let's watch a video. Okay? This is about the mole, because I really want to make sure we understand kind of conceptually what the mole is. We will write down maybe, yes. Let's write down 1 or 2 fun facts, okay? 1 or 2 fun facts. We're learning first.
Okay, today we're going to talk about mold. Now I know what you're thinking. I know what a mole is. It's a small, furry creature that digs holes in the ground and destroys gardens. And some of you might be thinking that it's a growth on your aunt's face with hair sticking out of it. Well, in this case, a mole is a concept that we use in chemistry to count molecules, atoms, and just about anything extremely small. Have you ever wondered how many atoms there are in the universe, or in your body, or even in a grain of sand? Scientists have wanted to answer that question, but how do you count something as small as an atom? Well, in 1811, someone had an idea that if you had equal volumes of gases at the same temperature and pressure, they would contain an equal number of particles. His name was Lorenzo Romano Amadeo Carlo Avogadro. I wonder how long it took him to sign autographs. Unfortunately for Avogadro, most scientists didn't accept the idea of the atom, and there was no way to prove he was right. There was no clear difference between atoms and molecules. Most scientists looked at Avogadro's work as purely hypothetical and didn't give it much thought. But it turned out he was right. By late 1860, Avogadro was proven correct, and his work helped lay the foundation for the atomic theory. Fortunately, Avogadro died in 1856. Now the thing is that the amount of particles in even small samples is tremendous. For example, if you have a balloon of any gas at 0 degrees Celsius and at a pressure of 1 atmosphere, then you have precisely 602 sectillion gas particles. That is, you have 6 with 23 zeros after it, particles of gas in a container. Or in scientific notation, 6.02 times 10 to the 23rd particles. This example is a little misleading because gases take up a lot of space due to the high kinetic energy of the gas particles, and it leaves you thinking atoms are bigger than they really are. Instead, think of water molecules. If you pour 18.01 grams of water into a glass, which is 18.01 milliliters, which is like 3.5 teaspoons of water, you'll have 602 sectillion molecules of water. Since Lorenzo Romano, never mind, Avogadro was the first one to come up with this idea, scientists named the number 6.02 times 10 to the 23rd after him. It is simply known as Avogadro's number. Now, back to the mole. Not that mole. This mole. Yep, this number has a second name, the molar. Chemists use the term mole to refer to the quantities that are at the magnitude of 602 sectillion. This is known as a molar quantity. Atoms and molecules are so small that chemists have bundled them into groups called moles. Moles are hard for students to understand because they have a hard time picturing the size of a mole, or 602 sectillion. It's just too big to wrap our brains around. Remember our 18.01 milliliters of water? Well, that's a mole of water. But how much is that? Exactly what does 602 sectillion look like? Maybe this will help. Exchange the water particles for donuts. If you had a mole of donuts, they would cover the entire Earth to a depth of 8 kilometers, which is about 5 miles. You really need a lot of coffee for that. If you had a mole of basketballs, you could create a new planet the size of the Earth. If you received a mole of pennies on the day you were born and spent $1 million a second until the day you died at the age of 100, you would still have more than 99.99% of your money in the bank.
Isn't that a little crazy? So he said, if you spent what?
$1 million every second.
Until you were age 100, you would have 99.9% of that left. Do you realize how large this number is? It's insane. It is huge. So if I said I held 18 grams of water in my hand, like that's probably 18 grams of water, people. How many molecules of water are in there? A mole of water, right? That's a mole. So 18 grams is about 1 mole of water. That is a million pennies spent every day of your, or $1 million spent every day of your life, every second, till the age of 100. That many little teeny molecules. So it's huge, and you just need to just wrap your head around that one part, and that should say, okay, this number is 1 mole, but 1 mole is just a phrase that means that number. Like a dozen means 12. So let's finish.
Okay, now we sort of have an idea how large the mole is. So how do we use it? You might be surprised to know that chemists use it the same way you use pounds to buy grapes, deli meat, or eggs.
We
When you go to the grocery store,
we don't have scales that measure in moles. We have scales that measure in grams, right, or pounds and whatnot.
you don't go to the deli counter and ask for 43 slices of salami. You buy your salami by the pound. When you buy your eggs, you buy a dozen eggs. When we hear the word dozen, we probably think of the number 12. We also know that a pear is 2, a baker's dozen is 13, a gross is 144, and a ream of paper is... Anybody?
How many sheets of paper?
A ream is 500. Well, a mole is really the same thing. For a chemist, a mole conjures up the number 6.02 times 10 to the 23rd, not a fuzzy little animal. The only difference is that the other quantities are more familiar to us. So there you have it, the story of the mole, Avogadro, basketballs, and how to buy salami at the grocery store.
Okay, I just briefly walked around looking for problem set 10. I didn't see a lot of it. Raise your hand if you've had problem set 10 with you. And you've gone through more than the true and false. Okay. Okay, I understand. But you guys need to bring it, because, I don't know what do you do during teal? Some of us work hard, some of us don't. You can do, 1 problem, 2 problems a day, and it's much more manageable than 15, 16, 20 at night, in one night. So, I thought I could trust that you guys some of us haven't practiced, I know for sure, because we still don't know what we're doing, and we've been doing this for 3 days. That's really sad, and I'm just going to tell you heart to heart. If you don't practice, if you pick up a basketball and you've never held a basketball before, you have no idea what to do. Same thing. If you don't pick up your calculator and try to calculate molar mass, you have 0 idea what to do. You have a quest on this on Tuesday. I hope that you take that to heart and do something over the weekend for yourself. Because problem set 10 is due Monday, but how do you expect yourself to absorb it that well in 1 day? Why do you think I assign it to do it over 3 days? I've done this for multiple years of my life. I know what you need. I'm trying to provide that for you, but if you can't at least take advantage of that, then I'm going to have to start taking up homework. And something like that, ask for a certain number of problems to be done every day, and I can. If that's best for you, I will. But I'm trying to give you some adult decision-making time here. You can make that decision for yourself. I don't have to force it on you, so you have to do 5 problems a day. But if you need me to, I will. I just thought I could trust that you guys would do that for me. So, those are heart to heart. Alright, so go ahead and start taking down some notes first. It's just somewhat disappointing because I have one class that's has actually most of the problems that's done, and in this class, I'm not so sure. So I am comparing honors to honors. I'm going to let you write down some stuff and then we'll talk. And then some of the questions we're doing today are on the lecture note sheet that you took. I gave you a couple days ago. You already took some notes on it though, so I'm not much space on the lines. we don't have very many today. We have like two big ideas: empirical formulas versus molecular formulas. We talked briefly about that with our reading guide 10. So we're really going to just be practicing problems, and then you guys can practice by your, with your partner in a little bit. Okay, so whenever you're talking about empirical formulas, so we'll get down here in just a second. When we're talking about empirical formulas, they are the easiest ratio. So I always think empirical is the easy one. It's the simplest ratio. And we've already done this, actually. If I said copper 2 sulfate, tell me your thought process of how to make that ionic compound. Okay, what are the charges, though? Copper's a 2+, sulfate 2 minus. We open that one. Okay, so you guys see that. You see the 2's, right? So in your mind, you're like, oh yeah, copper 2, and then the sulfate gets a 2. When you see this, okay, thank you. Okay, so when you get here, copper 2 and sulfate 2, what do you always do with this? What do you do with this?
Simplify.
You simplify, right? So what are you actually writing? CuSO4. So what are you actually writing? The empirical formula. You've already done this. You know what this is. It's just now we're like kind of getting more of the background about it. So the empirical formula is just the simplest ratio. So we would never write copper 2 sulfate like that because that's not how ionics are written. So anything that we've written ionically we already have the very simplest ratio. Therefore, that's called the empirical formula. Yes.
So wouldn't H2O2 be molecular?
Yes, because it's not simplified. So technically, H2O2 you can divide those numbers by 2, each of them, and that would reduce it down to HO. But that just looks awful, so we write hydrogen peroxide because that's the molecular formula. Anything that's that's a carbohydrate. For example, what's this carbohydrate? Glucose, right? Glucose, that is the molecule glucose, C6H12O6. But the empirical ratio for all carbohydrates are what? CH2O with a 1 and a 1 there. Because all of them have the greatest common factor. In this case, what's the greatest common factor in this case? 6. So you divide each of those by 6 and you get 1, 2 to 1. Yeah.
Okay, so when you're writing these out, would you put the 1 there as a subscript?
I can assume it's there.
Okay.
Yeah. So I'm just writing it for clarity's sake. Okay, so empirical formulas are something we're already familiar with. It's just the simplest ratio of the subscripts. Now, molecular formulas are, if I'm talking about a molecule, is that covalently bound or ionically bound? Covalent, right. Molecules are covalent. So if I had a covalently bound structure, that actually is a ton of carbons, a ton of hydrogens, a ton of oxygens for glucose again. This is the molecule. The molecule glucose requires us to have 6 carbons, 12 hydrogens, and 6 oxygens in it. But that's because it's the true, legit, actual molecule we're dealing with. We're not simplifying it. That simplification process is for easiness sake, for whenever we're trying to account for the ratio in which things exist. This is the true molecule. This is the true formula. And you'll notice if this is the molecular formula, so there's our molecular formula. This is the empirical formula. What is the multiplier on all of these subscripts to get back to that? 6. So an empirical formula can just be multiplied. I'm going to put a subscript of 6 out here. That 6 applies to everything within. So that multiplier gets me back to the molecular formula. Just like we divided up there, I just multiplied here. Whole number ratio, or whole number multiple, which applies the ratio. So this is going to make more sense once we actually do calculate some of them. But we have a step-by-step process. So instead of me just throwing questions at you, I try to come up with a how to solve X problem, right? How to solve empirical formula problems. It's right here. But this is going to be, oops, not this one. This is going to be your cheat sheet for how to do it until you're comfortable with understanding how to do it by yourself. Write down your cheat sheet, okay? So I try to do that with nomenclature and other stuff, and some people like the how-tos. If not, you're just kind of thrown to the wolves.
We don't want to be thrown to the wolves.
Just go down like right there, down 2. You'll use this a lot today. Just go like a big star by it, highlight it, what you gotta do. Okay, I'll come back down here once we talk briefly about the top. So whenever I ask for you to get to moles, what are some things I might give you so that you can convert to moles? Grams or liters. Okay, grams, liters. I'm probably gonna give you grams. Or what did we learn about yesterday? Those of you who were here. What did we talk about yesterday? Huh? Percent composition, right? So percent. I can give you grams of something, or I can give you a percent of something. So I might give you grams of copper, grams of sulfur, and grams of oxygen. And your job is to figure out what formula is this, what compound is this, based off the moles that you get and then the ratios in which they exist. So if I put C, S, and O together, what compound comes to mind? Copper what sulfate? Copper 2 sulfate, right? So some of these things are going to be familiar to you, but you're proving to me that this is right. So for example, if you found a certain white powder chromosine and you found out that it had so much of this, so much of that, so much of that, your job is to do analytical chemistry and figure out what compound it is. Maybe it kills somebody. I don't know, right? So there's real world applications. This is used all the time. Empirical formulas, molecular formulas. So once we are given grams or percent, your job is to get to moles by using molar mass or something else I'm going to show you with percents in just a second. Once you get to moles, you choose which of the 3, for that example, of the 3, which is the smallest number of moles, and you divide. Just like we did with the whole 6 to 12 to 6, what did we divide by? 6. So you're choosing the smallest one, and you're getting a ratio. And that ratio is then just subscripts. That's it, okay? So if once you divide, you'll get subscripts. Now those subscripts are usually close to a full integer, so you round it up to 1 or whatever it is. But the only time they're roundable, if it's 0.85 and up, or 0.15 and down. So those are specifics, right? Those are pretty, don't just like, oh, it's 0.7, I'm gonna round this up, right? That's kind of too far away for analytical sake, because we're talking about specific numbers here. So these are the different ways to get to a full number. So if it ends in 0.5, you're like, multiply by 2 to get to a full number. Got it. If it ends in 0.3, that's about a third. So if you multiply by 3, it should get you to a full number or a whole number. These other two are a little weird. You won't use them very often. More than anything, you're going to use that first one. So if I say we got like 1.55 moles of something, then you would multiply by 2 to round that up to about 3, 3.1, but still 3. So I think an example will shine through like what to do with this rounding thing more than anything. So on your the first one we're going to do is numero C on the empirical formula examples. C. Numero C. I don't know. So looking at this example, 120 gram sample. You guys see it on here? Everybody have this? Okay. So 120 gram sample of a compound containing hydrogen and carbon. Sorry. It contains 96 grams of carbon. What is the empirical formula of the compound? All right, so what do we know so far? What am I writing down in terms of givens? Okay, I know that I don't know what the sample as a whole is not that important. It's the components of it, right? Because we're trying to get these subscripts of the components. So we know one component to be what? 96 grams of carbon. What's the rest? How much? 24 grams of hydrogen. Because it tells you, it's a word problem, right? So you're reading, you're like, okay, this compound has carbon and hydrogen. You pull out the one piece of information you have. The other one is the difference between 120 minus 96, which is 24 grams. Got it? All right, so we basically just wrote down some given information. My job is to find the empirical formula. Look at your steps. What's the first step? Convert everything to moles. How would you do that from grams? So grams on the bottom, grams of carbon.
Then you do moles.
Okay. How many moles? 1 mole. So this is molar mass, right? You're using molar mass. What's the molar mass of carbon? 12.01. Yes, I want to hear more people than I hear 2 people right now. That's it. 12.01. All right, so I'm setting that up. I'm not going to calculate just yet. Same thing for hydrogen.
1.008.
So 1 mole of hydrogen is, on the periodic table, 1.00008 grams of hydrogen. So you should be looking at the periodic table probably 15 times a day, depending on how many problems you're doing, right? You're going to know where these things are. It should not take you long to find anything, especially something new, because you're looking at periodic tables so much now. So everybody calculate. Pull out that calculator. I don't care if it's a phone calculator. Pull it out. Let's get started. Yeah. I try not to, because if you round here, you're going to have a rounded moles here, and then you're going to divide, and it's going to be rounded, and then you're going to get a wrong answer. So try not to truncate your numbers too much. Plus, if it's on your calculator, you just go back and select, so it shouldn't be a problem. What's your moles of carbon? 7 point what? 9.4. I got 9. Is it 9.4 or 9.9? I got 9.9 when I did it, but you know, apples, tomatoes, tomatoes. Thank you. Sorry. Okay, this one. 23.80. Moles of hydrogen. Okay, so now we've gotten moles. Step 1 done. Step 2. So I'm just going to call it step 1 first, okay? What's step 2? Okay, so which is the smallest? 7.99. So I'm writing step 2 in green here. So I'm dividing by 7.99, dividing by 7.99. What's the first one? You don't need your calculator. 1. Second one, you might need your calculator.
Choose
2.97, almost right there, okay? So is that a roundable integer? I mean, number. Can you round that?
Yeah.
Right, because that's closest to 3. It's not like 0.85 and below. So I'm just going to scratch that and put 3 right there.
I thought we put it around it.
It is above 0.85. It is. It's 0.97. It's Friday, 4th period. I got it. Okay, so we have subscripts now, right? What's the formula? CH3, C1H3. There we go. There we go. That's it. Go to moles, divide by moles, get your subscripts. Empirical formula of this unknown white substance found on a crime scene that killed somebody. Okay, next one. Yeah, you guys do that one. You don't need me. Similar process. I don't believe I put this on your paper. No, so write down what you need to.
questions like this on your test.
I tried to print both of the examples, but sometimes I put extras. All right, so what you guys start with?
0.85.
You did what?
Then I minus 0.32.
Okay, so this
You
is.
know what?
I divided it. Okay. So I subtract or minus whatever. What? 0.32 grams of fluorine. Okay, and got how much copper? 0.5 what? 37 grams of copper. Okay. So that number for fluorine and that number for copper are the only two important numbers now. The total is simply a way to get to the other elements. Okay, so I'm starting off with my 0.321 grams of fluorine. Next. Times 1 mole of fluorine, 19 grams of fluorine. The more you participate, the more time you have for homework. As I chew on the gum.
No,
Not yet. Give me a second, okay? Stop. Okay, so what's this when you divide? You guys are calculating for me.
It's 0.0169.
One, say again.
0.0169.
One more number.
It'd be 0.0168.
6, 8, what?
9.
Okay, I'm pulling out like 3, 4, 5 decimals on the board for you because you'll notice there's 3 sig there. I need more than 3. I'm sorry, I need 3 in the end, but I'm not to the end, so I'm not going to round too soon. Next one, 0.537 grams of copper. What's the molar mass of copper? Okay, and what's that mole? 8,450 moles of copper. Okay, so I'm thinking molar mass should be second nature to you. You should be able to get from grams to moles in a jiffy. Okay, now we're to step 1. Step 1 has been done. Moles have been accomplished. What's next? Dividing by which one?
0.008.
So the 0.00845 for copper, 8845 or 00845 for fluorine and copper. So the lower one is what? 1 because it's a number divided by itself. Top one? 2 point.
It doesn't get a 0.15, so it's...
So tell me what the full number is.
Oh, actually, I did it with...
I got 1.9988.
That's what I want here. Okay, so 1.9988, something like that. But then you said, okay, well that's totally close to 2. That's going to be rounded to 2. So I'm just proving to you that we're rounding. I'm not just estimating. I'm calculating and then looking to see how close it is. So that's 2. So what are these numbers? They are the. Hold on, I will write that. But you know these are subscripts, right? These are the subscripts. And the way I've written it, I think half of us are going to go, oh yeah, F2CU. Doesn't that look ugly? If it looks ugly, it's probably wrong. Okay, so tell me how to rewrite that. CuF2. That it has a name. What's its name? Copper 2 fluoride. Okay, these things are going to be familiar to you on most occasions. There was one thing that we will do in your, it's going to be a huge organic compound. You won't know what it is, but you never write the metal. You never put the non-metal in the front. You just put the metal in the front. Yes. Yeah.
So you always divide by the larger number?
Smaller number. Just divide by the smaller number. You see 008 and versus 016.
Oh, after you convert. Okay.
Yes. Okay, so copper 2 fluoride. Thumbs up, you got that one. All right, let's do one with percents. So this is the one that I have not taught you how to do. Matt, let me see if they can come back to say one. Okay, so So whenever I give you a percent, this is what we learned a little bit yesterday. Percent composition. For example, I have a compound here with 94.1% oxygen and 5.9% hydrogen. If you assume a 100-gram sample, how many grams of hydrogen do I have? I mean oxygen. I have 94 grams. 94 grams of oxygen. So the percents are the grams. It's just I'm going to give you some of them as percents because that's a thing now, percent composition. And I don't want you to be like, oh my gosh, what do I do with the percent? Yeah.
So the favorite formula, you always assume 100%.
Yes. It's always the start. It's always the way that you start because you can't do crap with percent. You can do something with grams and then you can go on to moles. Yeah. Yeah.
So the only difference is just changing these percentages to the grams
And then continue like normal. Yeah, that's just the one extra step. So I wanted to show you how to do it first and then be like, there's another way I could expose it to you, but it's still the same process. So tell me what next step is here and next step is here. So 1 mole over 16 grams. So some of us are not even looking at our periodic table anymore because we got this. We know what oxygen is. Same thing here. 1.008 grams of hydrogen. Okay? Then our calculadora, what's this one? 94.1 divided by 16.
So it's literally 5.5.
Yep. Just the extra step up front. What is this?
5.88.
881 moles. Okay? This one?
5.8.
85. I don't have room for 3. There we go. Okay. So we got to step 1. Step 1 just took a little extra step because we had our little extra time because we had the percent. So you assumed a 100-gram sample, you went to grams, then to moles. Now what do you do? Divide by 5.85 because that's the smaller one. Divide by 5.85. So what is this? Approximately 5.88 divided by 5.85. About 1, right? Probably rounds down to 1, if anything. That's a 1, and this is definitely a 1. So what's the ratio? Okay, how should you write this? OH. And if I told you this had a charge, what would the charge be? -1. What is the name of it? Hydroxide. These things will be familiar to you unless it's a long organic one with a bunch of nonmetals, okay? So it feels doubly nice when you're like, I got it and I know the name. So double pat in the back, right? Because you know what these things are. Yeah. Because hosts are not in chemistry. We only have O's. That's why. Except for helium or whatever it is on the periodic table. HO. Where's it at? You know what I'm talking about. Right there. 67. That's the only one we have. And that's because somebody named it. Why would you name it? Okay, anyway, next slide. This is the last part, except for practice for today, okay? This is the last piece of information. And this should relate back to what we just did on the, for introduction to this. I'll let you right now what you need. So sometimes I'm going to ask you, after you find the empirical formula, also find the molecular formula. And remember, you may have noticed this previously, but in order to get to N, which is used to find the molecular formula, the very first thing you do is you first find the EF, because you cannot find the MF until you find the EF. You cannot find the molecular formula until you know the empirical formula. It's just how it is. And that's because, like previously, we had CH2O. We multiplied by 6. That 6 is a multiplier that goes inside to every subscript here to get C6H12O6. This is the what? EF or MF? EF. So what is the MF? C6H12O6. So that multiplier, though, I sometimes will give you the multiplier. I'll say the multiplier is 6 or whatever, but you can find the multiplier by using this little setup. And the way you find the multiplier is I will give you something called molecular mass or molar mass of the molecule. I'll give it to you, and I'll give you a hint. It's always the bigger number. Doesn't fail. It's always the bigger number on top. And then your job is using the empirical formula that you found. Tell me the mass of the empirical formula. Well, how do you find the mass of the empirical formula? Add them up. So, C plus 2 hydrogens plus oxygen, just from the periodic table. So it's something you've done before. So, but guess what? That's the bigger number. This is the smaller number. So you cannot get this wrong. So once you divide the big number, mass, by the smaller number, mass, you get this multiplier. And that multiplier you apply to the outside of the empirical formula and you distribute it in. Kind of makes sense? And I think an example will. Usually you're like, I have no idea what I'm doing until we do an example. Yeah.
So the mass of the empirical formula, you just do C2 or
Yeah.
CH2O, and you don't like do C6.
No, this is something I find from that. So I told you previously what it was, but you're finding this 6 by doing the math. So that's why it comes after the fact. Let me do an example. Let's do that. C, we're starting with, or no, B, whatever. B is on yellow paper. Oh yeah, it looks like this. I'm sorry, it's number 2. Empirical formula is C2H4 or S. With a molar mass of 179 grams per mole, what is the molecular formula? So what have I given you? I've given you the what? Molar mass. Okay, so the molar mass is 179 grams per mole, and I've given you the empirical formula. Why would I give you the empirical formula? Because I'm super nice, I'm not going to make you do it, but why is it important to finding the molecular formula? Okay, you just wrote this down. Because what? You divide by its...
You divide
the mass of... So you take the molecular mass, molar mass, and you divide by the empirical formula mass. So let's find the empirical formula mass. Calculator. 2 times 12.01 grams per carbon plus 4 times 1.008 for hydrogen plus sulfur 0.065. Add that up. How much you get? And normally I'm not going to write this out to you. I'm just literally telling you what to think of the calculator right now. 117 grams per mole. Okay, grams per mole is just the unit of choice for molar mass because that's molar mass, 2 units. Okay, so this right here is the empirical formula mass. That is the molecular formula mass. I'm going to then divide. I'm going to just at least make this look like a better fraction for you guys. So molecular mass over empirical formula mass is 179 grams per mole over what we just calculated, 60.117 grams per mole. What units cancel? Grams per mole. And that makes sense because a multiplier is a number, not a unit. It doesn't have a unit. So what's 179 over 60? 2.97, which is approximately 3. That is the multiplier. This is n. Okay? It's basically saying, like, how many times does this little empirical formula go into the molecular formula? So there's a multiplier here. So the big number over the small number gives us 3, but we're still not done. That's just the multiplier. How do I find the molecular formula? So you're doing C2H4S and multiplying what? By 3. That's N goes there. And so what's the MF? So whose light bulb went off? Like you see, the multiplier is simply a way, or the mass differences here are just a way to get the thing you multiply all the subscripts by. Okay, so this is the molecular formula because it can be reduced, simplified, or reduced, right? And that's the empirical formula because it can't. All right, let's do a harder one. That was the simple one because I gave you the EF. So, put on your crime scene investigator cap. Okay, we found this white powder, but we only found 0.400 grams of it. it happened to contain, after some mad chemistry skills, we found it contained 0.14 grams of potassium, 0.115 grams of sulfur, and the rest oxygen. Let's stop there. What can we do with that information?
Figure out the oxygen split.
Okay, and then finish reading. The empirical, experimental molar mass is blah, big number. What is the molecular formula of the compound? All right, so let's backtrack. If I want to find the MF, what do I need first? I need the empirical formula. But how do I find the empirical formula? Okay, we have to find oxygen first. Okay. We got grams of oxygen, grams of potassium, grams of sulfur.
And you do the
Get some moles, and then divide by the smallest. Find the subscripts. That's the EF. And then, how are you going to find the molecular formula once you know the EF? Take the molar mass,
divided by the
empirical formula, mass. Give the multiplier, and then multiply. Okay, that's nice to think through first before you begin, because sometimes you're like, what do I do with all these numbers? All right, so what do I do with all these numbers?
add potassium and sulfur and subtract.
Okay, how much you guys do that for me? I'm writing down these first two. So this is grams of sulfur, point what? 256 grams of oxygen. So we just took 0.4 minus that and that.
No, it'd be 100. It'd be 0.144 grams of oxygen.
Oh, I'm sorry. I see what you're saying. 0.144. Okay. Good start. We got some data. We got some information down. This is like number 3 on the paper in front of you. So, what are you multiplying each by? So their respective masses. So 1 mole of each of these. Their respective masses. I hope you're writing this example down. This is like the best example ever. Plus, it's the culminating one. What are their masses? Ian, tell me this one's mass. Hold up, man. Give me the mass first. 39.10 grams. Zach, give me the next mass. Yep.
32.
Okay. And Jillian, give me the last mass. 16 grams per mole. Okay. Everybody's calculating with me. Jamie, tell me the first moles. And Gia, tell me the next moles. And Ben, tell me the next moles. Jamie? Say it again. 3, 6. Give me more.
0.613.
Okay, I'm stopping here. It's good. All right, that's moles of potassium. Gia, you get me next.
0.00.
3, 5, 8, 7. I'm just extending these decimals out so we don't have rounding error. Ben? 009. I think it's like 00 if you had more digits recording on your calculator. Okay, so what essentially have we done for empirical formulas? That's it. We've gotten step 1 done. Wow. I know this is one step, but make sure you show me units and stuff, because I don't want you to forget that after this, we need to now do what with it? Divide. Okay, so we're dividing by smallest. Who's smallest? 0.009. So divide by 0.009. Divide by 0.009. Oh, I'm sorry. 0.035. My bad. Good thing I only had zeros there. 0.03587. 3587. Okay. And drum roll. What are these? Everybody. Hold on, I got this one. This is 1. Got it. What's this one? 1.03. And this one?
2.509.
2.509. Right? When you look at it, you're like, oh, it's like 9 over 3. You're like, oh, that's 3. Do not trust your estimation skills sometimes. That's 3. That 0.5 difference makes it not 3, makes it 2.5. So this is the first time we've seen not a full integer, right? Not close enough to round. So go back and look at your notes, or maybe just think about it. What should I multiply all of these by to get them to full integers? 2. So I have to multiply this one by 2. But if I multiply this one, that means I change the ratio, and I'm not allowed to do that. I have to keep the ratio the same. So if I multiply this one by 2, I got to multiply this one by 2, and this one by 2. So what are the new, yeah? Because 2.5 cannot be rounded up or down. 2.509 is in the middle, so our job is to get it to the next integer by multiplying, not rounding. And that was on the very first page notes. Yeah.
So you should multiply the 1.03 by 2 and then round it after?
Yes, we'll round it at the end. Yep. So but when you multiply that by 2, it's 2.06, right?
Yeah.
Well, that's just 2.
I was wondering, like, if it was a higher number,
Then you would round.
if it would change the rounding.
I will not do anything that complex.
Okay.
And so this is 5. So then what we have now is the empirical formula of what? Give me the empirical formula. K S2O5. So that's kind of like potassium thiosulfate. It's actually potassium peroxysulfate, but that's close enough. We see that K goes first. That's pretty much what matters. So we've got the EF. We've only really dealt with the first sentence. Second sentence. Tell me what I do. So take that mass, that big mass, right?
Yes.
Divided by what? The mass of this. What was it? 859 grams per mole.
Yes.
Divided by, somebody add this up. Everybody add this up. Mhm. So potassium is 39.10 plus 2 sulfurs of 32.065 plus.
174.
That's not what I got. That's right. I think you forgot one of the subscripts here. I got 222 point. Huh? Yeah. Okay. So this is the EF mass down here. This is the molecular mass up here. What do you need to divide? Okay, thank the Lord it's above 3.85. What do we do with that?
Round it up to 4.
Round it up to 4. So N is 4. Okay, big deal. What does that mean?
That's your multiplier, so you do that times the EF, and that gives you the empirical.
Right. So you take this N and you put it over here and you multiply out. So tell me the new formula, the molecular formula. KAS8O20. Whew. Big compound. That's some sort of new drug on the streets. I don't know. That's what we found it.
It's a white powder.
It's a white powder. We all know white powders are bad. Baking soda. Hard stuff. Okay. Do you feel better about EFs and MFs?
Yes.
Okay, you have a process. This is for you. But I will do you a favor, and I will chop this down to necessities, bare necessities. You have more to do if you need more practice. But I want you, number 2, no, that would be like disservice to you in your education. 2, 4, 1, and 4. I brought Tim down to 4. You're welcome. But please get that done right now. You have 20 minutes. That's 5 minutes a question. It should not take you more than that. I'm expecting you to get it done, actually. I'm expecting you to get it done. Yeah. Okay. If you are working with a partner and you do not work, I'm going to give you a detention. Let's just call that even. I need you to work for it.
I'm looking at me too. Me too. Sorry, I love you. I love you too. But I got to work there. I work better by
This is on your paper, by the way. It's not your handout. This thing. So you don't have to look for it. One molecule makes the allocated to add so you're using more of a
I am.
one molecule.
Oh, that's a few. One more. I did some.
Divide that by 0.81915 and right? What? 0.819. Yeah. And then the next one's 828.
I wanted to see how that would be normal. That's what I do.
Oh, yeah. Then you divide that.
I think so, yeah. I don't know. And then some of the always observatories we learned today. So would it just be 4? Yes. 4.0. 0, 0. Yeah, I think
Yeah, that's it.
you have one aluminum phosphate.